Immutable structures. Grow, tag, reboot. Have you ever heard the saying, just because we can do something doesn't mean we should? I can't think of a more relevant saying in software architecture. When we encounter a complex problem, the best solution is to avoid it altogether. My favorite tool to reduce complexity and to solve difficult problems is with immutable data structures. Let's get started by looking at the classic memory management problem. Take a heap. And let's exercise this heap by allocating blocks. This linear memory allocation is the kind of allocation we'd see at the startup of a program. So far, so good. But over the runtime of an application, fragmentation occurs. As blocks are allocated and deleted, we end up in any number of complex memory states. It's important to note that this is not a deterministic process, meaning it changes from runtime to runtime of an application. In the example in front of us, we have about 100 megabytes of free memory, but we can't allocate a 30 megabyte block. This is the memory management problem. Conventionally, it's solved through garbage collectors in managed memory languages and systems. That is to say that pointers are dereferenced, so the memory underneath of them can be relocated to resolve such a problem. It is important to remember that this problem arises every time we allow for the allocation and deallocation of a resource. As software architects, we need to remain aware of this fundamental principle and understand its role in the formation of complexity. Let's take a look at how this principle impacts a B tree, the complex sibling of a binary tree. Implementing a balanced algorithm for a binary tree is enough trouble. It's a whole different kind of trouble for a B tree. If we allow for both insertions and deletions from our B tree, we will have to be constantly balancing and refactoring the tree. I've implemented several B trees. It's always fun, up until the point when you have to take into account balance and deletion. It goes from being intuitive and enjoyable to being a headache and a nightmare. This brings me to my point. Just because we can do something doesn't mean we should. And I've grown to believe that certain data structures are better off left immutable, or in this case, grow only. No, this doesn't apply to every data structure, but where it does, we should pay attention and utilize immutable data structures. In practice, this works by allowing the data structure to grow to a certain size. Instead of deleting data, we tag it, indicating that we're not using it anymore. When our data structure reaches its size threshold, we reboot. What I mean by reboot is we rebuild the data structure from the ground up, excluding the tagged entries. Something fascinating happens when we employ this in our architecture. The complexity and size of our source code plummets. I believe that that is the sign of a successful architect, when the amount of code we have and its complexity is reduced. The best source code is no source code. We don't have to write it, we don't have to maintain it, we don't have to debug it, and we don't have to ship it. To summarize, architecture. What goes wrong? Complexity. A common source of complexity is immutable data structures. For example, our binary tree. Insert is easy. Balance is okay. Delete is hard. This stems from the memory management problem. Heap fragmentation is a real thing. Just like disk fragmentation. You'd be surprised how many people don't know programs crash, slow down, or fail due to this. We can avoid balancing our trees altogether by hashing our branch indicator with a properly distributed hash. We can avoid deleting by managing our data lifetimes and scope at the architecture level. We don't delete data, we tag and migrate. It just so happens that this works for the same reason rebooting your computer works. Rebuilding a data structure from zero is much simpler than managing a multi-threaded read, write, delete, update state. Utilize this technique. Build reboots into your architecture, databases, and data structures. It's a time-honored, time-proven method. Do this with immutable data and migration. One final note about immutable data structures is that they are much faster. The reason being is it's much easier to parallelize access to simpler data structures. I've utilized all these principles in a database I've implemented named TemplateDB. You can use it anywhere you'd use something like SQLite, LMDB, or Memcached. Have a look for yourself. Thanks for watching.